Okay, lesson 2 of chapter 5 talks about geometric proofs. Now, before we start this, let me just say this. Whenever I was in school, geometric proofs were taught in high school. It was in my geometry class, which I believe I took my junior year. Now, the reason I'm taking it down memory lane here is just to say that it's something that is completely new to you. It is a higher level skill. It's a higher level concept. Some of you may struggle with it. Others may have no problem with it whatsoever. So there's only one lesson on it. Do your best. I'm going to be flexible in your answers, flexible in your reasoning, but I do just want you to try and think at a higher level whenever we do this. So with that being said, let's get into it. So first of all, we need to talk about some vocab right here on this page. Let's talk about inductive and deductive reasoning because that will be in the lesson later and it will also be like in the examples. So if you talk about inductive reasoning, it's the process of making a conjecture. So like a hypothesis, a guess, a theory, a thought. It's a process of making a conjecture after observing several examples. So you watch a example that goes over and over and over and over and over, and you get to think about a pattern and you can put your own thought on it and make an opinion on it. Now, deductive reasoning uses facts and rules and definitions and laws to make conjectures, theories, thoughts, guesses, hypotheses from given situations. So this talks about observing and taking your observations, and you kind of put your own thought on it after you make several examples. See several examples. Deductive means that, well, you just use known facts, things that have already been stated before, things that are accepted to be true, definitions, laws, theories, and you use those to defend your position. So that's the difference, and that's what we're going to be using today. So let's go on and get to the lesson here. Nice little detective, one big eye. All right, so let's talk about the proof process. So a geometric proof is basically you arguing that something is true based on justified reasons. Not, well, this angle is a right angle because it looks like it is. No, you have to have some proof, some rule, some thought, some theory that actually is widely accepted and that states to be true. Use that as your evidence. Just like if you went outside and say, oh, it's cold today. Well, your definition of cold and somebody else's definition of cold may not be the same thing. But if you set a glass of water out on the sidewalk and you come back in an hour and it's frozen into ice, definitely be cold. That would be a widely accepted fact. All right, so a proof is a logical argument where each statement is justified. That's the key to proofs. They have to be justified by a reason. So two different kinds of proofs. The first one that they talk about is called a paragraph proof. Paragraph proof is more informal. It's just where you write sentences to state your reasoning. So it involves writing a paragraph to explain why a conjecture, why a theory, why a thought is true. So we've got, it says in example 1 below, you will use the algebraic property of substitution, which is just putting something in something else's place, and the geometric relationship between vertical angles. Now, in the first lesson, I talked to you about several different types of angles. Remember, alternate interior, alternate exterior, corresponding, all that kind of good stuff. I believe we talked about supplementary, but just real quick, I did not want to overload you last time with angles. So there are a couple more that I want to talk to you about real quick before we move on through this. So make sure you take notes of this. All right, let's say we have two lines that cross, say like that. Okay, there are another type of angles, vertical angles. Now, normally you think about vertical being up and down. Okay, in geometric means we're talking about angles that are directly opposite each other. They are, more formally, they're non-adjacent angles that meet at a vertex. Non-adjacent means they're not next to each other, so there would be space in between. They do not share a common side, and they have equal measures. So if I told you that this one was 120 degrees, then you would automatically know that this one is 120 degrees. Now, with that also being said, we talked a little bit about supplementary angles. So angles that come together to make a straight line. So if I've got part of that line right there, right, part of the angle, to go the rest of the way to meet that line right there, those are supplementary supplementary angles form a straight line, and there are how many degrees in a straight line? 180. So if I know that this is 120 degrees, then that means this angle right here has to be 60. Why is that? Because I know that these are supplementary, they form a straight line, and a straight line has 180 degrees in it. That's kind of the justification we're going to get to in these proofs. I know that this angle right here is 60. Why? What would be my justification? Well, it's vertical to this one. It's directly across, it meets at that vertex. This angle right here, this angle right here, they do not share a side. They're directly across from each other. In the room, I have a poster that talks about mirror images of each other. If you could take this one and fold it over to here, right? This would be a 60-degree angle. 60. So that's supplementary. They add up to 180 degrees, or they make a straight line, however you want to talk about it. Now, only one other one that I want to talk to you about would be lines that form a right angle. So, out of this right angle right there, let's say I've got my little box that denotes that that's a right angle. If I know that, let's say this one is a 70 degree, right? This angle right here is 70 degrees, then what would this one be? Well, if I know that they add together to get 90, and that's 70 of it, that leaves 20 for this one, all right? So these are called complementary. Now, this is spelled a little bit different than the other kind of compliment. We're not giving somebody a compliment like, ooh, your hair looks nice. Ooh, the shirt looks good on you. Pink is your color. No, this is complementary with an E, complementary. It means it adds to, right? So they form a 90-degree angle. Complementary angles form 90 degrees. So, a couple other definitions. Let's talk now about some geometric proofs. First one here, the diamondback rattlesnake has a diamond pattern on its back. An enlargement of the skin is shown. If measure of angle 1 equals the measure of angle 4, write a paragraph proof to show that measure of angle 2 equals the measure of angle 3. So what they are looking at here, they are saying that angle 1, which is here, and angle 4 are equal. So if measure of angle 1 and measure of angle 4, you have to prove that 2 and 3 are. You cannot just say they're equivalent, they're equal because they look like it. So you have to use some kind of geometric proof, all right, geometric reasoning. We're going to use the vertical angles that we just talked about, right? Vertical directly across from each other. So if 1 is vertical to 2, that means 2 and 1 have to be equal. 4 and 3 vertical, so that means these are equal to each other. So if 1 and 4 are equal, and if 1's equal to 2 and 4 is equal to 3, then that means 2 and 3 have to be equal. So that's what we talked about here. Measure of angle 1 equals the measure of angle 2 because they are vertical. Just talked about that. Since measure of angle 1 is equal to the measure of angle 4, because that is given, measure of angle 2 and the measure of angle 4 are equal by substitution. So it's just saying that if this is equal to this, and this is equal to this, then therefore 3 and 4 are equal. All right, so wrap your head around that for just a minute. All right, top of the next page, I want you to go ahead and pause it, try it, and then we'll come back and we'll do this one together. Okay, so there are basically fill in the blanks that they're asking you to do. Okay, and you've got to fill in the blanks here, 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 all these blue lines. So this is what we're looking at. It says, refer to the diagram shown, AR equals CR, they're talking about the lengths of the segments there, and DR equals BR. Write a paragraph proof to show that when you add two of them together, you equal the other two. So, given AR equals, you get it right from here, AR equals CR. And DR equals BR. You get that straight from there. That's under the given part. You have to prove, again, we get that right from here. Show that, so you have to prove AR plus DR equals CR plus BR. So you know that AR equals CR and DR equals BR. So AR plus DR, AR plus DR equals CR plus DR because of the addition property of equality. Addition. addition. So AR plus DR equals CR plus BR by substitution. Now, this is what I mean by that. Let me get it written out here. Okay, so what they're saying is that if this equals this, right, AR plus DR equals CR plus DR, so if this and this are the same and they are equal, what it's saying is that what if you're adding the same thing to both sides? That's where the addition property of equality comes from. So therefore, you're saying it could be equal to each other because these are equal also. So there's your substitution. All right, let's go on to two-column proofs. These are a little bit more formal. These are ones I actually remember from high school, you know, way back in the Stone Age when we wrote on stone and used a chisel and had to worry about being eaten by dinosaurs. Yeah, otherwise known as the 80s and 90s. All right, so two-column proofs contain statements and reasons organized into a column and table. So it's not just writing things out. You actually have to fill in a chart on these. So once a statement or conjecture has been proven, it's called a theorem, kind of like the Pythagorean theorem, which we'll be getting into in a few lessons. And it can be used as a reason to justify the statement. So you cannot just say, oh, this happens over here. It has to be proven before you can use it as a reason. All right? So let's try number 2 here. It says, write a two-column proof to show that two angles are vertical angles, then they have the same measure. So you are going to prove that. So given, this is the easy way to start any proof. You always have to say what's given because you have to introduce it into evidence, kind of like in a courtroom. You have to introduce it into evidence before you can use it as a reason for a defense. All right? So given lines M and N intersect. That would be my first thing I put on here. Lines M and N intersect. Also, angle 1 and 3 are vertical. Angle 1 and 3 are vertical angles. Your reason for stating this is just that it's given. It's given in the problem. All right? So now it says angles 1 and 2 are a linear pair, and angles 3 and 2 are a linear pair. Now, what does that mean? That means that they form a line. 1 and 2 form a line. 3 and 2 form a line. So that's the definition of a linear pair. That's what that means, that they form a line. All right, so moving on to our third reason. Measure of angle 1 plus the measure of angle 2, 180. Measure of angle, whoops, sorry, I should have muted that. That's an email coming in. Measure of angle 3 plus the measure of angle 2 equals 180. So that's the definition of supplementary angles, which again, to me, is the same as a linear pair. So if it were me, I probably wouldn't have written this one. I probably would have skipped right to this. I would say, okay, I know that 1 and 2 are supplementary. I know that 3 and 2 are supplementary. Therefore, 1 plus 2, so putting these together, is the same as 2 plus 3 because they both equal 180, right? We just proved that right here. And what is that? That is substitution. That's something that you're going to have to get used to putting in there as a reason. It is substitution because you can substitute one side in for the other because they are both equal. So what if I had this as, let's say, like an equation? Couldn't I subtract the measure of angle 2 from both sides? Subtract it, what would be left? Measure of angle 1 is the measure of angle 3. And that is my subtraction property of equality. And that we just proved what it wanted us to prove. It said prove measure of angle 1 and measure of angle 3 are equal. And they are vertical angles. This angle and this angle. They are vertical. Okay. Let's try some more. Pause it and try it under got it, please. And then we'll come back and work it together. Okay, let's look at our statements here. It says measure of angle y equals the measure of angle z. Measure of angle y equals 2x minus 90. Measure of angle z equals x plus 10. And I told you the start of these always going to be the easiest. The reason is that it was given. All of that information was given right here in the problem. Okay, it's all given. So 2x minus 90 equals x plus 10. Well, if I know that these two are equal, and this equals this, and this equals this, well then surely I can put them in there. They are equal, and I know that by substitution. I can substitute one in for the other. Again, remember you gotta Get that word out there. That's because it's going to be the answer quite a few times. Now, if I have this equation, we've been solving ones like this for a long time. Couldn't I just subtract x from both sides? Right? If I subtract x from both sides, wouldn't I end up here? So what reason would that be? Subtraction, property of equality. Man, handwriting is atrocious on the board. Whew. Now, what have I got here? If I had an equation that looked like that, would I not add 90 to both sides? Add 90 to both sides? That would cancel this out. 10 plus 90, 100. How I get here? And it's the addition. I'm putting a period there because that is my abbreviation. Property of equality. Okay. So with that, that is proofs. Again, try your best on these. Use some reasoning. Always make sure to start a proof with what? What is given. All right? Come see me with any questions. Good luck.